Hello everybody. I've been gone for a while. It's been very difficult to find time to record. So this is my first video after maybe a week or so. Let's see if we can continue a more regular basis, posting a more regular basis. Okay, so today we're going to do a whole range of problems. They all have to do with capacitors. You probably know, usually you find two metals that form a capacitor. Capacitor means the devices which can hold charge. Okay, so what can hold charge? You can have a like a metal of any shape, like this, a metal, and you can put some positive charge on it, so it's holding power. So it's a capacitor. But normally capacitors are usually we deal with two metals, some other metal. So this is metal A and this is metal B, and we maybe would transfer some electrons from here to here, and this become a same amount of charge, negative, as becomes positive. So usually we'll deal with capacitors which have two metals. They call each metal is called metal plate, although over here they're not really plates. They're like this spherical ball, and there's another spherical ball shell, and this is like a metal rod, and then a cylindrical shell. So it doesn't have to be a plate. It's just there are two metal pieces, but each piece is called a plate. So this would be an example of a capacitor. So this will have a charge plus Q, and this will charge minus Q. And you probably know that each metal, the entire metal in electrostatics, is at one potential. This one is some potential B plus with respect to infinity, and this is V minus with respect to infinity. So there is a voltage difference between them. Now if this is air here, say this is air, suppose this air, then if I keep putting more charges on these guys, eventually voltage difference will be so large that you'll start to get a spark from here, maybe. So electrons will jump from here and go over there. So there's a capacity of charging these plates, and so there's a quantity called capacitance that we associate with when we have two metals. At what voltage, how much charge means how much voltage. Okay, so capacitance of this is the ratio between the charge it can hold. It's holding plus Q here and minus Q here, but we just call it Q, just Q, and the voltage difference is V plus minus V minus. So voltage difference is delta V equals to V plus minus V minus. So charge and V, their ratio is called capacitance, and it's usually written in a capacitor formula. Is called this two-plate system is called a capacitor. It can have multiple plates, can have more than two plates, but usually you can deal with two plates. A capacitor formula, and this Q refers to charge on one of them because they both have the same amount of charge except oppositely signed. So this is Q, usually is positive, and C is called capacitance. The ratio of this to this is capacitance, and delta V is just V plus minus V minus. It's important to know that this formula, you remember, is Q equals CV, but then this V is actually a difference between the positive plate and the negative plate. And we're going to work out what the formula for C should be under different conditions. Okay, so for instance, if you have two large plates and you have then the formula of capacitance is this. And because this plate is going to be large, we're going to assume infinitely large. So it's better to think about charge per unit area rather than charge is proportional to area like that. Because this area happens to be infinite in our assumption. When we do this formula, this area will be assumed to be very large, practically infinite for us. Okay, so we're going to use that assumption to find this formula. This formula, you memorize it, but you should know how to get this, because once you know how to get this, usually the problem will be that I fill with a dielectric, or maybe I filled with two dielectrics. So between the plates, I have some part is filled with one dielectric or dielectric constant Ke1, another one dielectric constant Ke2. I'll fill it that way, or I can fill the other way. So the distance, the width is same, but the area that it fills is different. So this guy has a volume A1 times D1, and this guy has volume A2 times D2. A2 times D. They have the same D. Okay. So let's work out these formulas. I'm going to erase this and work one at a time. Okay. Okay. So here's a system. We have two plates. So this is plate A, and this is plate B, and we're going to make one of them negatively charged and another one positively charged. And then we're going to say what's the voltage difference, so I can take a ratio. So this one will have a minus sigma, and this will have a plus sigma. And this area is infinite. So it's like sigma times A minus sigma times A is minus Q. And of course, A is infinite. So this makes really no sense. Q is going to be infinite. But we're going to say we can do this. Sigma times A will be plus Q, with a Q standing for a positive number. Okay. The reason we use minus sigma plus sigma is because we know in electrostatics, B at point P minus V some reference is equal to minus from reference to P E dot dl. We need to do this integral, right? So we need, if I can figure out electric field, I can do this integral. So if I figure out electric field between these 2 points, at some arbitrary point here, I can do an integral from negative to positive plate using this negative reference as the negative. Sure enough, if you have a plus sigma and minus sigma and infinitely large plates, then the electric field at any point P is basically going to go from positive place towards negative place. Electric field pointed that way, and electric field has a magnitude sigma over epsilon naught. Okay, and this is going to be constant, and so I go from here to there. Then this integral will be V plus minus V minus is going to be wherever the minus is, where the plus is, and I do E dot dl, right? So if this is a z-axis, let's call it z-axis, and call this at origin. So this is going to be, and they're in the opposite direction. So I'm going to go from 0, and this is going to be D. I'm going to 0 to D, and this is going to be just this E, sigma over epsilon naught dz, which is just going to be sigma over epsilon naught times D. So if you remember, capacitance formula is Q equal to C delta V. Or if you have an sigma, then Q over area equal to C over area times delta V. So this is delta V, this is delta V, and if you look at that, this is Q over A. So this is Q over A times D over epsilon naught. So if I compare this with that, you can see that Q over A equals to Q over A is equal to, I can send this on the other side, epsilon naught over D times delta V. And so this should be equal to this quantity. So C over A equal to epsilon naught over D. Although A is infinite in all of this, I can assume A large but finite. Say A large but finite. We can just write it like this: A epsilon naught over D. So that's and the same process will go in other cases also. Okay, so we're gonna do the other cases now. Okay. So we do exactly the same thing. We are going to put a plus sigma on minus sigma on this side and the plus sigma on this side, and assume a area to be infinite. It's the area of the plate, this area, the surface area facing it, right? Area is A is that area, surface area. Okay, so now what's gonna happen? Well, electric field over here will be pointed that way. Electric field here points, so electric field is pointing in the same direction, but over here the electric field will be reduced by dielectric constant. So this will be epsilon naught sigma sigma over epsilon naught Ke, and over here sigma over epsilon naught Ke2, Ke1 and Ke2. It's Ke2. So now when I'm going to do integrate, when I integrate from let's see, start from here, Z, and this is D1 plus D2, and this is D1 and this is O. So integrate from here to there, I get so say there was a V1 here, okay, and this is the reference, which will be 0. So I go from O to D1. This gives me V1 equal to this electric field sigma over Ke1 epsilon naught D1, and I go from D1 V1 minus V at O, which is we're going to take at 0, and D1 to D1 plus D2, I'm going to get V at this second plate, V plus minus V1 equal to sigma over Ke2 epsilon naught D2. So this is V minus, this is V minus. So if I add these guys together, I get V plus minus V minus, V plus minus V minus. V1 cancels out when you add this, and you get a sigma over epsilon naught, and you get a 1 D1 over Ke1 plus D2 D2 over Ke2. And so this is, you can say this is Q times A, Q over A. This is called Q over A, epsilon naught, and you have this stuff. And this side is delta V. So Q over delta V will be will be the capacitance will be Q over delta V. So working this out, I'm going to get epsilon naught times A. So this is A over epsilon naught. So this goes on the side, and this whole thing inverse of that times D1 over KE1 plus D2 over KE2 inverse. So that's the answer that you would get. There is a shortcut to this I want to illustrate. The shortcut is very kind of cute. You just put a plate here, two plates, so to say, right on top of each other. So here minus sigma, this plate, this side is a plus sigma, and this side minus sigma. It's the same plate, and you can think of this as one capacitor and this as another capacitor, but they are in series, right? So you have a C, let's call it C1, and let's call it C2. C1 is going to be from before epsilon naught A over KE1 D1, and C2 will be epsilon naught A over KE2 D2. And when capacitors are in series, the equivalent capacitance adds this way: 1 over C is equal to 1 over C1 plus 1 over C2. So let's look at that way. Call it 1 over C. 1 over C will be, you can write down here 1 over epsilon naught A, and the inverse of that will be just itself. D1 over KE1 plus D2 over KE2. So you can see I can distribute it, and you can see D1 over epsilon naught A KE1 plus D2 over epsilon naught A KE2. And so this is as if this guy was capacitor by itself, and this is a capacitor by itself. This is 1 over C1 plus 1 over C2. So I could just do this trick and get the answer, same answer, or I go more fundamentally and do the integration and try to seek. So when seeking delta V, from which get Q over delta V, get Q over delta V, and that will be the C. I'm going to identify that as C. Let's try this one for the next problem. Okay, so this problem is kind of very similar. So if I take a path, from this point, say this point, and go into that point on the other plate, and I can take another point from here to over the other side. Okay, so let's call it path 1, let's call it path 2. So I go here from here to here, but the plates are, I'm going to get the same V plus minus V minus, the same, I'm going to get same if I go this path or that path. With this path, I'm going to get sigma over epsilon naught KE1, that's the electric field here, times D, and that's going to be sigma 1, because in this area it's going to be sigma 1, and then should be if I go in the other area, sigma 2 over epsilon naught KE2, same distance D. Okay. So if let's do something more here. Multiply by A1 and divide by A1, multiply by A2, divide by A2. So let's also just denote this by a V for simple manipulation. So you can see that this is I'm going to call it, this is Q1, charge on this side, over, you can say C1, and this whole thing I can do the same way, and you can see that's some C1 as if it was just by itself. So Q2 over C2. But the total charge on this whole plate versus other plate is total charge is Q1 plus Q2. And we want ratio of V divided by total Q. So we want V over Q1 plus Q2, right? So, and so V is this thing, so let's work this out. V can be, let's look at the inverse of this, Q over V. Then you have a Q1 plus Q2 over V, and you have a Q1 over V plus Q2 over V, right? We really want a Q equal to CV, so we want Q over V, and we don't want this, so we want Q over V. So we get this, and so Q1 over V from here gives me C1 and gives me C2. So this is the C that I want for the total charge on the two plates. So this simply turns out to be epsilon naught A1 KE1 over D plus epsilon naught A2 KE2 over D. So I need to know how much of the area is each one of this material is occupying, you know. So I have to tell you what this area for at the plate is for this material versus what that for that material, and then so that will be the answer. So C here is simply actually a formula. You can think of that these two capacitors were in parallel. So like this capacitor were parallel, then C was like as if I had two of them added together. So this is also called capacitors in parallel. This, unlike the other previous example, which is in series, and which just gave me epsilon 1. I'm going to write KE1 this way, and then A1 over D plus epsilon naught KE2 A2 over D. If they're half and half, then you know you can just write down A1 equals to A2, which is half of A. But this way you get a more general formula. Okay. All right. So we covered both the cases of filling the gap with dielectric materials in a couple of different ways, and let's look at an example where it's not parallel plate capacitor, but maybe a spherical capacitor. How would we do that problem? Okay, so we have two spherical shells, and we want electric field between them. If I charge one of them, say this is say minus Q, and this is charge plus Q. Okay, so it is a sigma minus here, and over here is sigma plus. Of course, sigma minus is minus Q, and this is the area is 4 pi. Maybe let's call this R1, and this is R2, R minus and R plus. Let's call it R1, R2. R2. 4 pi R1 square, and sigma plus is plus Q over 4 pi R2 square. Okay. We need to find electric field at an arbitrary point. What's the electric field over here? Well, we already know it's going to be pointed towards this center, in that way. Another way was the magnitude of that. So we use Gauss's law to figure out the electric field. So we apply Gauss's law. And I'm not going to repeat the argument, but if this is some radius r, so you have a 4 pi r square, and the magnitude of the electric field will be same all around, that's going to be how much charge is enclosed, which is q is minus q over epsilon naught, right? So the electric field will be just this, and it will be pointed that way. So how do we get how do we use this to actually we want to do v plus minus v minus, so minus what the minus is, what plus is E dot dl. So one way to do it is let's call this a z-axis. So this is just a z component. So I go from here, z equals to r1 to z equals to r2, and I just go from here to there, and I go in opposite direction. So just like before, v plus minus v minus is going to be just from r1 to r2. This quantity, this r will be just some arbitrary point, will be z, is going to be minus q, just a q over epsilon naught 1 over 4 pi z square dz, right? So let's do this out. So you have a q over epsilon naught 4 pi, and this is z to minus, so 1 over z, this is minus 1 over z, r1 to r2, and so this just simply becomes q over 4 pi epsilon naught. This one will go first, 1 over r1 minus 1 over r2. So because of minus, I just use this, and then I use that, and this is just a v, or delta v. And so we're looking for q equals to c delta v. To read c, we just look from here. So in this formula, this is simply 1 over c. So so c just turns out to be 4 pi epsilon naught 1 over r1 1 over r2. Make sure this r2 is greater than r1 here, inverse, and that's the answer. So I want you to see that, and I needed to know the electric field, and I had to do this in order to get that answer. And so if you learn how to think at it in a fundamental way, you will be much better off. You can do this problem, other similar problems. Okay, there's one more problem we can do. Okay, so we'll come to that. Okay, so this is an infinite cylindrical shell. So again, let's see, this thing has a charge density which is lambda coulomb per meter now, right? And this will be, let's call it a minus, and so lambda inside, so lambda inside like that, and lambda outside plate is like that. You have same length, so they will be the same, because they're the same. Unlike the sphere, there were different charge densities. Here they will be the same, because I'm giving lengthwise. This is, why do I lengthwise? Because this is cylindrical symmetry. I can use Gauss's law. I need electric field here. So this is my positive plate, and this negative plate, and so electric field pointed towards the center. Okay, that's the direction of the electric field. And what's the magnitude of electric field? Magnitude will be just, we can imagine a Gaussian, let's use use a different color. So from here, suppose this is a distance s from this axis, then the electric field will be the same on all this point on the surface in magnitude wise. And so this surface area and the electric field flux through that is going to be electric field. I'm going to convert that into magnitude, so everything will be positive. So 2 pi s times 2 pi s, and let's take a height arbitrary. This is arbitrary height L. So this electric field magnitude wise, and then minus lambda, total charge enclosed is times L. So this is the charge enclosed inside this, times epsilon naught. The electric field on this surface, this is flux is 0, and the bottom part flux is 0. Now these are more detail in the Gaussian chapter, right? So-called Gauss's law, where you get lots of electric field in lots of symmetric situation. You can study the video earlier we did, or you can go to physicsbootcamp.org to study more on that. So suppose I got this. Now I want to do the integral. How would I do it? How would I set it up? Well, I just like to just say this is the z-axis and this z equal to 0. So I just go from this point to that point, and the electric field is exactly opposite. It's very easy to do then. So at any point is along the z-axis, the integral will be along the dz, and you have electric field. Electric field will be, this is lambda L over epsilon naught times 2 pi SL. Conveniently L cancelled out because L was arbitrary, okay? So E dot dl becomes this, and I need to integrate from, let's call this R1, and let's call this R2. So I want R1 to R2, and so this is going to be delta V will be plus minus V minus will be that, and that's going to be lambda over S is actually Z here now. S, the distance from this is actually Z, arbitrary point Z. So this gives me lambda over 2 pi epsilon naught log. This with this gives me log R2 over R1. And of course R2 is greater than R1, and so this has to be positive. So this is positive, as it should be, plus minus positive. Make sure your things are in the right way. Okay, now I have a delta V equals to lambda over 2 pi epsilon naught log R2 by R1. Now because this height is infinite, I can only think in terms of a finite distance. So let's call this L here. So this will be, so I put L up and down, and so this becomes the Q on this, in this area, Q up to here, Q on that part of the cylinder, okay? And we are looking Q equals to CV, right? So this over this, C delta V. So we're looking for Q over delta V, and then what you get? You get you have to send this on the other side, 2 pi epsilon naught L over log R2 over R1, right? I think I did correctly. So this should be equal to, this will be equal to C from this formula, right? But there is an arbitrary thing here. L is arbitrary. So instead of saying C, we'd say, in these cases, we say C over L per unit length. And that will be 2 pi epsilon naught over log of R2 over R1. So that's the answer. Okay, I think we covered a lot of ground today. Hopefully you learned something from it. You like these videos, then you should give a like to this. Hopefully you can subscribe to this channel so it can expand its reach. And you can also go check out my website where this kind of way of presenting physics, you can get more of it. Okay, have a nice day. Okay, bye.